This is Dr. D. Govardhan, Professor and Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today topic is discussion on tutorial question bank, Module 4, Particle Dynamics and Work Energy Principle. First we are discussing the D'Alembert's principle. It is named after this French mathematician and physician Jean-Le D'Alembert. It is the alternate form of Newton's second law of motion. According to D'Alembert's principle, when the number of forces are acting on a body, if the body moves in the direction of x as shown in figure, that means the resultant of all the forces also having in the direction of x as shown in figure. The resultant of all the forces can be determined by using two methods, graphical method and analytical method. That means if R is representing the resultant of F1, F2, F3, F4, which are acting on a body, having mass m, if it is a move in the direction of x with an acceleration of a, then according to the Newton's second law of motion, we can represent it as R is equal to m into n, where R stands for the resultant of all the forces, m is the mass of the body, a is the acceleration in which the body is accelerating. So here now, the direction of R as well as the direction of motion of the body both are in the same directions, or in other words, the body is always moving in the direction of resultant of F1, F2, F3 forces which are acting on a body. This R is equal to m into a. It can be modified as now R minus ma is equal to 0 now. Here that means the body is moving, the external forces are also acting on it. But according to the problems, R minus ma is equal to 0 means the resultant forces here it is treated as 0 now. When the system of forces are acting on a body, if the resultant of all the forces, if it is equal to 0, then the body is said to be in equilibrium. But here is also in equilibrium. But if the body is at rest, that is called static equilibrium. When the body is moving, it is called dynamic equilibrium. Hence, this equation can be stated as now. Here, when the system of forces are acting on the body is always in equilibrium positions with the inertia force. That is minus ma is treated as inertia force. That means the D'Alembert's principle states that the system of forces are acting on a body when it is in motion. So it is always in dynamic equilibrium with the inertia force of the body now. That is R minus ma is equal to 0 now, where minus ma is representing the inertia force of the body. So this equilibrium is called dynamic equilibrium because the forces are acting on the body. The resultant is also equal to 0, but when it's in motion. This is the most important equation for analyzing the forces in engineering field, such as when the forces as well as the acceleration, the terms are involving in it. So the main application of the D'Alembert's principle are in the areas of lift, connecting bodies, motion of the two bodies connected by string, passing over the smooth pulley. Here D'Alembert's principles, we can solve we can analyze the forces which are acting on the body when the forces as well as the accelerations, if it is no. Here, based on that equations, we are having certain problem we are discussing. The problem number one is an elevator of a mass of 500 kg is ascending an acceleration of 3 meters per second square. During this ascent, it is operator whose mass is 70 kg is standing on the scales placed on the floor now. What is the scale reading? What will be the total tensile forces in the cable of elevator during the motions? Here the given data is the elevator of the mass is equal to 500 kg. Acceleration is given 3 meters per second square. Mass of the operator 70 kg. Here first one we are taking now. The pressure exerted by the man when the lift moves upwards with an acceleration of 3 meters per second. So when the body is moving now upward directions, here assume this is our elevator. Here now, the weight of the man is acting downward directions. And inertia force is always acts in opposite directions to the body is accelerating. According to the problem, here we are taken the body is the elevator is moving in upward directions with an acceleration of 3 meters per second. Hence, inertia force is acting in downward directions. And let R be the representing the reactions in the cable. So when I apply in D'Alembert's principle, that is the resultant of all the forces always in equilibrium with the inertia force acting on it. This MA is nothing but representing inertia force, but here in opposite direction given, hence that is shown in the figure in downward directions. When we are taking the resultant now, that is R is equal to mg acting downward directions plus MA is also acting downward directions. Only R is the acting, that is the tension in the rope is acting upward directions. That means when it is equilibrium position means the sum of the forces which are acting in upward direction should be equal to the resultant of all the forces which are acting in downward directions. That is R is equal to mg into MA or M into G plus A, which is equal to 896.7 newtons. Now the tension in the cable of the elevator now, if it is representing, it is equal to, already we have taken here mg plus A now, where capital M is representing the total mass of the person as well as the cage, which is equal to M plus M now into G plus A now, which is equal to 7301, that is 7301.7 newtons. Here we are taking another problem. A cage carrying 10 men, each weighing 500 newtons, starts moving downwards from the rest in the main vertical shaft. The cage attains a speed of 12 meters per second in 20 minutes. Find the pressure exerted by each man on the floor of the cage. Take G is equal to 9.80 meters per second square. The given data in the problem is the weight of one man is equal to 500 newtons is given, but total 10 men are now traveling in the cage. So the total weight is given by 500 into multiplied by 10, it is equal to 5000 newtons. Initial velocity of the cage is equal to 0. It will attain a speed of 12 meters per second in 20 minutes. Hence we are taking final velocity is equal to 12 meters The distance traveled is equal to 20 meters is given. Acceleration due to gravity is g is equal to 9.80. The pressure exerted by the man on the floor of the cage will be same as the pressure exerted on the floor by the man now. So R is equal to pressure exerted by 10 men on the floor, which is also equal to the pressure exerted by the floor on the man. Now A is equal to acceleration of the cage. The acceleration will be obtained by using the equations, that is v square minus v square is equal to 2as. From this relationship we got to A is equal to 3.6 meters per second square. When a cage is moving in downward directions now, here it is we taken, that cage is there, it is moving in downward directions. Here the weight of the persons as well as the cage is acting in downward directions. Since the cage is moving downward directions, the inertia force is always acts in opposite directions, in which the body is tending to accelerate. So it is upward directions, which is equal to W by G into A. And R assume it is nothing but tension in the rope, it is also acting upward directions. Now, when they are equating according to the D'Alembert's principle, the resultant force should be equal to 0. The algebraic sum of the forces which are acting in the direction of motion is equal to 0. That means here the forces which are acting in opposite directions generally we are taken as positive forces, in downward directions negative. Hence here R, that is the tension in the rope, W by G into A, it is called inertia force, minus W is equal to 0. From this relationship we got R is equal to 500 into 1 minus 36/98, which is equal to 3163.26 newtons. The pressure exerted by the floor on one man is equal to R by 10, which is equal to 316.326 newtons. Here problem number 4 now. A man weighing 750 newtons stands on the floor of a lift. Find the pressure exerted on the floor when the lift moves upwards with an acceleration of 3 meters per second, and the lift moves downwards with an acceleration of 3 meters per second. That is, in two cases we have to determine the pressure exerted by the man on the floor now. Okay, dynamic equilibrium can be obtained by applying the inertia force. Here we are considering upward motions. The body, when it is moving, here the cage is there. The body is moving in upward directions now. That is, in the direction it is moving. Inertia force is acting in downward directions. Assume T is the tension in the rope, it is always acting in upward directions. The weight is acting in downward directions. So here now the upward forces are T plus MA. T is the tension in the rope, it is always acts in upward directions. Since we have taken here now the body is moving in upward directions, inertia force acting in downward directions now, it is equal to T minus W by G into A minus W is equal to 0 now. That is T minus MA minus W is equal to 0 now. So from this relationship we got the tension in the rope is equal to 979.3578 newtons. Similarly, when the body is moving upward directions now, downward directions, we got inertia force is nothing but acting upward directions. Tension is also upward directions, so weight is acting downward directions, which is equal to T plus MA minus mg is equal to 0. From this one, mg minus MA is equal to M into G minus A. that is 753 divided by 9.81 into 9.81 minus 3. On simple calculations, we got to 520.264 newtons. Here, an elevator of a cage of mine shaft to 8 kilonewtons when in empty is lifted or lowered by means of a wire rope. Once a man weighing 600 newtons entered it, lowered with uniform acceleration such that when a distance of 187.5 meters was covered, the velocity of the cage was 25 meters per second. Determine the tension in the rope and the force exerted by the man on the floor of the cage. Take G is equal to 9.8 meters per second square. Here the given data in the problem is the weight of the elevator cage is equal to 8 kilonewtons. Initial velocity of the cage is equal to 0. The distance travelled equal to 187.5 meters. The final velocity was 25 meters per second. The acceleration due to gravity is given G is equal to 9.80. Since according to the D'Alembert's principle, R minus MA is equal to 0, hence first of all we have to determine the velocity acceleration of the moving body. So by using the relations, V square minus V square is equal to 2AS. So from this relation now we got to V square. U square nothing but initial velocity is equal to 0. That is V square minus U square is equal to 2AS. 2A into S is equal to 187.5. From this relation we got A is equal to 1.667 meter per second square. Here the cage is moving in downward directions now. Hence when we are drawing free body diagram of the cage and applying inertia force on it, here the weight is acting downward directions now. The reaction force is always act upward directions. Direction of inertia force is always act in opposite direction in which the body tends to accelerate. That is the upward directions now. And applying according to the D'Alembert's principle, tension is nothing but positive. That is here now. Acceleration force is equal to W by G into A minus W is equal to 0. From this relationship we got here R is nothing but it is equal to tension T. Now from this relation we got to 7138.9 newtons. This is the tension in the rope now. Let the pressure exerted by the floor on each man is same as that of the pressure exerted by each man on the floor of the cage now. Let R be the force exerted by the man on the floor, R the reaction force exerted by the floor on the man. Then R in nothing but it is acting upward directions now. W by G into A, it is acting again upward directions, minus W is equal to 0. From this relationship we got the reactions offered by the floor on the man is equal to 498.06 newtons. The problem number 6. An elevator of a cage of mass 900 kg when empty is lifted or lowered vertically by means of wire rope. A man of mass 72.5 kg is standing in it to find the tension in the rope, the reaction on the cage on the man, and the force exerted by the man on the cage for the following two conditions. When the cage is moving with uniform acceleration of 3 meters per second square, when the cage is moving and down with a uniform acceleration of 3 meters per second square, with uniform velocity of 3 meters per second. So case 1, here assume the body is moving in upward directions now. Here mass is given 900 kg, mass of the cage, mass of the man is equal to 72.5, upward acceleration is equal to 3 meters per second square now. Let T be the tension in the rope in newtons. Since it is moving in upward directions now, the inertia force is always acts in downward directions, which is equal to M into A, where M is nothing but representing the total mass of the cage as well as the person. Here weight is given, hence total weight is equal to capital W plus small w divided by G, that is called mass, multiplied by A, it is equal to inertia force. But it is acting in downward directions. The tension is always acting away from the object, but it is upward directions now. The total weight is equal to capital W plus small w now. As the cage moves upwards, according to the D'Alembert's principle, T weight is acting downward directions now. Capital M plus small m into G. Acceleration is again it is acting downward directions now. M plus capital M into E now. Okay, from this relationship we got to T is equal to 12,458 newtons now. In case 2, consider the various forces in the equation is for regarding reactions. R minus mg is equal to ma, where R is equal to mg into plus ma. From this relationship we got the reactions offered with the cage is equal to 928.7 newtons. When the cage is moving with a uniform velocity, that means A is equal to 0. That is A is acceleration which is equal to rate of change of velocity. Since when it is moving with the uniform velocity, the acceleration is equal to 0. Let T be the tension in the rope now. So in applying D'Alembert's principle, we got to T is equal to here M plus M into G. Here the body is moving in upward directions, downward directions. The inertia force is acting. When the body is moving upward directions, inertia force is acting in downward directions. Tension is upward directions, weight is also acting upward directions. Here, the sum of the forces which are acting in upward direction should be equal to the downward directions. So from this relationship we got to, that is a T, nothing but when the body is moving, inertia force is acting downward directions, weight is acting downward directions. So from this relationship we got to, we can evaluate the tension in the string now. When the body is moving in downward directions now, the reaction forces are it is also at upward directions, tension T upward directions, weight in downward directions. Then putting these equations we got to T is equal to M plus M into G minus of M plus M into 0, because A is equal to 0. We got tension is equal to 9,540 newtons. Okay, these are the simple problems we have taken for the application of elevators now. Now taking just connected bodies. When the two bodies are connected together means these two bodies always move with the same velocity. The acceleration is also the same now. In most of the cases, these two bodies are treated as single body for evaluating forces. Otherwise, we can consider it individually by putting the reactions of tension within the string now. Here the problem is the two bodies of masses 80 kg and 20 kg are connected by a thread and move along the rough horizontal surface under the action of force of 400 newtons. Applied to the first body of mass 80 kg as shown in figure. The coefficient of friction between the sliding surfaces of the bodies and the plane is 0.3 now. Determine the acceleration of the two bodies and the tension in the thread by using D'Alembert's principle. Here I am considering first the second body. This entire system of bodies are moving toward the right hand side now by the application of 400 newtons force. Here first considering the 20 kg body. It is also moving toward the right hand side due to the tension in the rope now. The forces which are acting on 20 kg, that is the free body diagram is represented as now. The 20 kg is nothing but T is nothing but tension. It is acting toward the right hand side now. The weight is acting downward directions 20 kg. The frictional force is there now. It always acts in opposite direction in which the body tends to move or the moving. It is along the surface. Hence, F is equal to, we can take it as mu into N2, where N2 is representing the normal reactions between the contact surface of the bodies. So, which is equal to mu is equal to 0.3, coefficient is given now, 20 kg is given. Here, 20 kg is nothing but representing here now. Mass is given. Here the word is given, it is the masses of 80 and 20 kg is given. Hence, weight is equal to, it should be multiplied by 9.81. So, which is equal to 58.9 newtons. This is the frictional force is acting now. Now, for determination of T now, first of all, the body is nothing, just we have to take, let A be the representing the acceleration which the body is moving now. Now, applying D'Alembert's principle for the first body. Here, since the body is moving toward the right hand side, the inertia force is acting in upward directions now. That is, this is directions, which is equal to M into A, that is 20 into A. This is another acceleration, that is inertia force. Tension it is there now. Friction force is again acting in opposite direction now. So here now, the vertical forces, that the weight as well as the normal reactions, both are balanced with each other. Hence, when you are applying D'Alembert's principle, generally it is always in the direction of motion of the body, which is equal to the right hand forces is assumed positive and negative, left hand forces are negative. Hence, according to the D'Alembert's principle, the algebraic sum of the forces always in equilibrium with the inertia force now. So, T positive, it is given now, and inertia force minus 20 into A, it is negative. Friction force is also minus F negative, it should be equal to 0 now, which is equal to 400 minus 80 into minus 20 into A now, which is equal to 0. From this relationship, we got A is equal to 1.057 meter per second square now. So, this problem can be solved by assuming the two bodies are treated as a single body, or by separating the two bodies by drawing a free body diagram. Okay, here now we solved this problem, determined E by assuming that the two bodies 80 as well as the 20 are treated as same now, because they are moving with the same acceleration now. Hence, we have taken this is equal to A is equal to 1.057 meter per second square now. So, the forces are applied now, 400 newtons. Inertia force is equal to 80 plus 20 into A. Friction force is equal to 0.3 into 80 plus into 981 is given now. Plus, for the second one is also there, 20 load now. And applying D'Alembert's principle, we got to is a force now. Tension in the thread between the two masses is equal to, here consider any one of the object only. Now, I am taking just in figure number 2 here now. That is for the 80 kg body. The 400 is nothing but the force which is applied toward the right hand side positive. Tension is always negative for the second one. Here, M into A, since the body is moving toward the right hand side, the inertia force is equal to M into A. M is equal to mass 80. A is equal to 1.057. The friction force is always acts in opposite direction into the body tends to move. Since we are considering the body to now, that is 80 kgs, so which is equal to 0.3 into 80 into 9.81. That is F is equal to F2 is equal to mu into N2 now. Where mu is equal to 0.3, N2 is nothing but balanced with the weight. Weight is equal to 80 into 9.81. From this relations we got T is equal to 80 newtons. Problem number 8. A 750 newtons crate rest on a 500 newtons cart. The coefficient of friction between the crate and the cart is 0.3 and between the cart and road is 0.2. If the cart is to be pulled by a force P such that the crate does not slip, determine the maximum allowable magnitude of P. The second one is the corresponding acceleration of the cart now. Let A be the accelerations when the cart is moving, just without slipping. That is important here now. Is about to slip, maximum we are taking. So for the sigma y is equal to, when we are drawing free body diagram now, for the crate, the forces are acting, that is 750 newtons acting downward directions now. And the friction force which is present between these two, F1 is acting toward the, because it is most toward the right hand side, the friction force is acting here now. N1 is the normal reactions now. Taken. From this relation, so N1 is equal to W. W is equal to how much it is? 750 newtons is given. F1 is equal to mu into N1, 0.3 into 750 equal to 225 newtons. So sum of the sigma Fx is equal to 0 according to the D'Alembert's principle, which is equal to 225. It is nothing but friction force is acting toward the left hand side now, which is should be equal to M into A, where M is equal to inertia force now. That is 750 divided by 9.81 into A. From this relation we got A is equal to 2.943 meter per second square now. Now consider the dynamic equilibrium of the crate and cart as a single body. The total weight is acting, it is equal to 1250 newtons now. That weight is acting. Normal reaction is equal to N2 is equal to, is acting upward directions now. Since the cart is moving toward the right hand side by the application of P force, hence here P is given, friction force is acting in opposite directions in which the body tends to moving now. The inertia force is always acts in opposite direction in which the body is moving now, or accelerating, which is equal to 1250 divided by 9.81 into A now. Since there is no slipping between the crate and cart, hence the total weight is treated as the weight of the cart as well as the crate both are treated as, and the sum is treated as single body, which is equal to 1250 newtons. So sigma y is equal to 0 since the body is moving in a direction of applied force. So sigma y is equal to 0. From this relationship we got Nt is equal to 1250 newtons. Friction force is equal to mu 2 into 0.2 into 1250. It is equal to 250 newtons. Sigma Fx is equal to 0. That is the algebraic sum of all the forces which are acting in the direction of motion is equal to 0. That is according to the D'Alembert's principle. The resultant force which is acting on the body is always keep the body in the equilibrium position, equilibrium condition with inertia force. Hence, sigma Fx is equal to 0. That is minus P, it is acting toward the left hand side now. Plus 250, that is frictional force is acting toward the right hand side now. These two. The inertia force is there, it is again acting toward the right hand side because the body is moving toward the left side. It is equal to M into A, where M is equal to here, the weight is given 1250, that's why we are dividing by 9.81 into A is equal to 2.943. From this relationship, we got to the minimum force is equal to 625 newtons. Here we are considering that is a pulley system here now. Let determine the tension in the string and the acceleration of the blocks A and B, weighing 1500 newtons and 500 newtons connected by an inextensible string as shown in the figure. Assume pulleys are frictionless and weightless. Now consider the here pulley which is having weight is equal to 1500 newtons. Here the forces which are acting on it now. Let T be the tension in the string, it is acting upward directions. Here it is also acting in upward directions. T plus T, it is equal to resultant is equal to T, acting upward directions. So the 1500 newtons is acting in downward directions. Since other end it is having 500 newtons now, hence the 1500 newtons body always moves in downward directions. Or in other words, the inertia force is acting upward directions, which is equal to 1500 newtons, that is mass when you require 9.81 into A, it is acting upward directions. Now according to the D'Alembert's principle, the body should be in dynamic equilibrium. That means the sum of the forces are always equal to 0. So upward forces are positive, that is 2T, the positive. Inertia force is also acting upward direction positive, that is 1500 divided by 9.81 into A, which is equal to 1500 or minus 1500 is equal to 0. That is the sum of the forces acting upward should be equal to the downward now. Similarly for this second body, since the body is moving in upward directions now, the inertia force is acting for this one is the downward directions now. Downward. So the forces are there now, here now. In the block when we are taking, here for the block tension is acting upward directions now. The weight is acting downward directions, but the body is also moving upward direction, means inertia force is in downward directions now. That is the T positive, inertia force is negative, that is 500 divided by 9.81 into 2A. It should be minus of, it should be equal to 0 to 8.9. Here, if A is representing the acceleration within the 1500 newtons, body is moving downward directions. But 500 newtons moves with the double velocity, double acceleration. Hence, we have taken it is equal to 2A now. Okay, solving these two equations, we got A is equal to 1.4 meter per second square and T is equal to 642.89 newtons. Okay, work energy principle now. When the system of forces are acting on a body, earlier which is at a point A, because of application of the force, the resultant force, assume just is gone to up to B position within the time T and also by traveling a distance of S. Let U be the representing the initial velocity of the body, V is representing the final velocity of the body at B position. According to the work energy principle, the work done by the forces should be equal to the change in kinetic energy of the body. Work done is equal to force into distance, where force is the resultant of F1, F2, F3 and F4 forces which are acting on the body. Hence, R into S is equal to the force into distance is equal to change in kinetic energy is equal to 1 by 2 m into v square minus v square, where m is representing the mass of the body, v is representing final velocity, u is representing initial velocity. So, by using this principle, we can analyze the forces which are acting on the body when the forces, initial velocity, final velocity and the distance parameters are involved. Here, based on work energy principle, calculate the work done in pulling up a block of mass of 200 kg for 10 meters on a smooth plane inclined at an angle of 50 degrees with the horizontal. Calculate the work done. Here, mass of the block is equal to given 200 kg. Distance is equal to 10 meters. Inclination of the plane is given, alpha is equal to 15 degrees is given now. So here now, let P be the representing the force which it is applied along the plane. Weight W is representing the weight of the body. It can be resolved into two components now, the vertical component and horizontal component. This vertical component of weight is balanced with the normal reactions N2 which is acting in upward directions. Since it is moving along the smooth inclined plane, hence the friction force which is acting on the body is equal to 0. Hence N2 is equal to, we can take it as here N2 is equal to, and take it as W into cos alpha. The weight component it is there now, which is acting along the plane is equal to W sin alpha. It always tends to move the body in downward directions. So the resultant force is equal to here P minus W into sin alpha. So work done is equal to force into distance, that is P minus W sin alpha into S. We require this is the equation. And so from this relationship we got to the mass is given 200 kgs now. It is equal to, so the weight component which is acting along the inclination of the plane is equal to mg sin alpha. 200 into 9.8 into sin 50 degrees is equal to 507.2 newtons. The work done is equal to resisting force multiplied by the distance, which is equal to 5.072 into kgs. The problem number 10. A locomotive draws a train of mass 400 tons now, including its own mass, on a level ground with uniform acceleration until it acquires velocity of 54 km per hour in 5 minutes. If the frictional resistance is 40 newtons per ton of mass of the engine, and the air resistance varies with the square of the velocity, find the power of the engine. Take air resistance as 500 newtons at 18 km per hour now. Okay, the given that in the problem is the mass of the locomotive is given now 400 tons now. Here 400 tons is given, including its own mass is given. The velocity acquired is equal to 54 kilometers per hour. So it is 54 kilometers per hour means it is equal to 5 by 18. It is equal to 15 1 ja 15 3 ja. It is equal to 15 meters per second square, that is equal to A values now. That is velocity is equal to 15 meter per second. The time t is equal to 5 minutes, which is equal to 300 seconds. Frictional resistance is given now. That is 40 newtons per ton now. So 40. Total weight is given 400 newtons into 400, which is equal to 16,000 newtons. Generally, it can be rated as 16 kilonewtons now. Let A be the acceleration of the locomotive. Here now, the final velocity of the locomotive after 300 seconds. It is equal to 15 and equal to, that is according to the here 15 is equal to U plus 80 now. From this relationship we got to V is equal to U plus 80. A is equal to 0.205 meters per second now. The force required for this acceleration is equal to M into A now. That is 400 into A is equal to 0.05 equal to 20 kilonewtons. A resistance varies with the square of the velocity now. The A resistance at 54 km per hour is equal to 15 meter per second. So R is equal to, again we are taking now 500 into, that is equal to, it is just depends on the square of the velocity now. 500 into 50 square divided by 18, which is equal to 4.5 kilonewtons now. The total resistance is equal to 16 plus 20 plus 4.5. It is equal to 40.25 kilonewtons. The work done in 1 second is equal to the total resistance multiplied by the distance now traveled in 1 second, which is equal to 40.5 into 15, which is equal to 607.5 kilonewtons per kilonewton meter per second, which is equal to 607.5 kilojoules per second. The power is equal to rate of doing the work now. That is rate of doing the work, which is equal to 607.5 kilowatts now. A locomotive and a train together has a mass of 200 tons and a tractor resistance force 100 newtons per ton now. The train can move upgrade of 1 in 125 with a constant speed of 28.8 km per hour. Find the power of the locomotive. Also find the speed which the train can attain on a level track with the same tractor resistance and the power of the locomotive. Here the given data in the problem is mass of the body is given, that locomotive and train together it is equal to 200 tons now. Tractor resistance is nothing but a friction resistance is given 100 newtons per ton, which is equal to 100 into total weight is given 200 now, which is equal to 100 into 200 is equal to 20,000 newtons. It can be written as 20 kilonewtons now. The grade is given 1 in 125. It is nothing but in the form of, it is moving like this now. It is given. If you take this 125 means it is given in 1 now. That is 125. It is a 1 now. So sin alpha is equal to, we can take it as it is alpha is there, that is the inclination of track now with the horizontal. Sin alpha is equal to 1 by 125 now, which is equal to 0.008 now. The train velocity is equal to 28.8 kilometers per hour. It can be written as now 8 meter per second now. The power of the locomotive. The resistance due to the inclination is equal to here now. Because the weight is acting, is in the directions now, perpendicular. It can be resolved into two components now. That is, when you are taking the weight, nothing but the two components, we can take it now. So the resistance due to the inclination is equal to mg sin alpha. This is equal to 200 into 9.8 into inclination is 0.008 now, which is equal to 15.7 kilonewtons now. So the total resistance force is equal to resistance force plus resistance to the inclination now. It is equal to 20 kilonewtons plus 15.7 equal to 35.7 kilonewtons now. The work done in 1 second is equal to the total resistance force multiplied by the distance traveled in 1 second. It is equal to 35.7 into 8 meter per second, which is equal to 285.26 kilonewton meter per second. It can be written as now 285.6 kilo Newton meter per second is equal to joules per second now. So it can be written as in terms of power equal to 285.6 kilowatts now. Speed which the train can attain on level track. Here earlier we have taken inclination now. That is the weight component which is acting in downward directions, that is also oppose the motion of the body. That can be treated as 0 since it is now in second case moving along the horizontal track now. So thus it has overcome the resistance now, which is equal to now the power of the locomotive is equal to 285.6 is equal to track to resistance and the speed of the train now. It is equal to 20 into speed of the train we have to take. That is the additional that is given earlier now. That is this 15 can be eliminated now. So from this relation, speed of the train is equal to 285.6 divided by 20. It is equal to 51.5 kilometers per hour, or it is equal to 14.3 meter per second now. Okay, problem number 12. An engine of mass 50 tons pulls a train of mass 300 tons up an incline of 1 in 100. The train starts from the rest and moves with a constant acceleration against total resistance of 50 newtons per ton. If the train attains a speed of 36 kilometers per hour in a distance of 1 kilometer, find the power of the engine. Also find the tension in coupling between the engine and the train. The given that in the problem is the mass of the engine is given 50 tons now, and the mass of the train is equal to 300 tons. The total mass is equal to 50 plus 300 is equal to 350 tons now. Since the slope is given now, it is moving just on a track which is making inclination of alpha is given. That is sine 1 in 100 now. That means when it is moving just 100 mm length now, the height is moving just 1 mm now. Or it is nothing but equal to sine alpha is equal to 1 by 100 now. That is sine alpha is equal to 1 by 100 is equal to 0.01 now. Initial velocity is equal to 0. The tractor resistance is equal to here 50 newtons per ton is given now. Total weight is given 350 newtons. Answer 50 into 350, which is equal to 17,500 newtons, which is equal to 17.5 kilonewtons per 17.5 kilonewtons. Final velocity is equal to 36 kilometers per hour, which is equal to 10 meters per second. That is 36 into 5 by 18 is equal to 10 kilometers. Distance traveled is equal to 1 kilometer. From this relation, we have to determine what is the acceleration. That is m into a we require now. That is the acceleration is equal to 350 into a is equal to 0.205, which is equal to 17.5 kilonewtons. The total resistance force is equal to tractive resistance, resistance due to the inclination, force required for the acceleration now, which is equal to 17.5 plus 34.3 plus 17.5, it is equal to 69.3 kilonewtons now. The work done in 1 second is equal to total resistance force and distance traveled in 1 second, which is equal to 69.3 into 10 now, or 693 kilonewtons meter per second, which is equal to 693 kilojoules per second, or 693 kilowatts now. Tension in the coupling. It is a tension which is responsible to pull the train by the engine. Generally, it is an equipment which is connects the train as well as the coupling now. The tension is always active within the coupling now. The tractor resistance is equal to, for train only we are taking now, 50 into, because it is pulling only the train, 50 into 300, which is equal to 15,000 newtons or 15 kilonewtons. Similarly, the resistance due to the inclination is equal to mg sin alpha. It is equal to, for the second one, mg sin alpha, which is equal to 300 into 9.8 into 0.01, 29.4 kilonewtons. Force required for the acceleration is equal to, that is 300 into 0.05, that is it is moving with an acceleration of 0.05. The mass is given 300 and 15 kilometers. The total tension in the coupling is equal to, that is total force which is acting just away from the coupling, which is equal to 15 plus 29.4 plus 15, which is equal to 59.4 kilonewtons. This work energy principle is also applicable in springs problems also. Here, a wagon of, problem number 13, a wagon of mass 15 tons start from the rest and travels 30 meters down a 1% grade and strike a post with the bumper spring as shown in figure. If the rolling resistance to the track is 15 Newton per ton, find the velocity with which the wagon strike the post. Also find the amount by which the spring will be compressed. If the bumper springs compresses 1 mm per 20 kilonewton force. Okay, the given data within the problem is the mass of the wagon is equal to 50 tons now. Initial velocity it is equal to 0 because it starts from the rest. And distance traveled is equal to 30 meters in downward directions, that is S is equal to. The gradient is equal to 1%, that means when it is moving just under distance like this, it is equal to 1 now, 1 by 100, which is equal to 0.01. Track resistance is according to the problem, if the rolling resistance to the track is 50 Newton per ton now, that is 50 Newtons. Ton is nothing but the weight of the wagon is given 50, that is 50 into 50 is equal to 2500 Newtons. That we can write it simply 2.5 kilonewtons. The bumper spring constant is equal to 1 mm per 20 kilonewtons. So it can be written as 0.05 mm per kilonewtons. Now first we determine just velocity with which the wagon strike the post now. Let cap small v representing the velocity with which the wagon strike the post. The gravitational force, since it is traveling along the inclined plane, so the weight is acting in downward directions now. It can be resolved into two components now. One is acting toward the downward directions, which is balanced by the normal reactions offered by the surface. W sin theta, this is nothing but always pull the body in downward directions. So which is equal to mg into sin theta. Here mg is equal to 50 into 9.8 into 0.01, which is equal to 4.9 kilonewtons. The net force responsible for moving the wagon is equal to gravitational pull is equal to downward direction, friction force is acting upward directions now. So which is equal to 2.5 kilonewtons. That is 4.9 minus 2.5. It is equal to, the resultant force is equal to 2.4 kilonewtons now. The net force responsible for moving the wagon in downward direction is equal to 2.4. Generally, it should be equal to m into a now. So 15 to a. From this relationship, we can get the values of a is equal to 2.4 divided by 50, which is equal to 0.048 meters per second. So by using the relations v square minus v square is equal to 2as now. Since the final velocity is now, initial velocity is equal to 0, it is coming from the rest now. That is, we can treat it as now 0 plus 2as, 2 into a is equal to 0.048, s is equal to 30. From this relation, the final velocity is equal to 2.88, that is v square is equal to, v is equal to 1.7 meter per second now. The amount by which the spring is compressed now. Let us assume here after traveling a distance of x, it is coming to the rest position now. The kinetic energy of the wagon is equal to 1 by 2 mv square is given. It is equal to 1 by 2 into 50 into 1.7 whole square. It is equal to 72.25 kilonewtons meter, or it can be written as now 72,250 kilonewton per mm. So compressive load is equal to x divided by 0.05, it is equal to 20x now. Work done in compressing the spring is equal to average load multiplied by the displacement, which is equal to 20x by 2 into 10x square. It is nothing but work done by the spring force. From this relationship, we got x is equal to 85 mm. So the D'Alembert's principles is the conclusion of this. D'Alembert's principle is it is used to solve the forces or analyze the forces when the acceleration as well as the forces which are acting on a body. Similarly, the work energy principle is useful for us for solving the forces when the force, accelerations, initial velocity and final velocity and the distance moved, that is the involved now. So based on the parameters which are given in the problems, we can use the work energy principle or D'Alembert's principle to analyze the forces which are acting on a body. Okay, this is the conclusion of the work energy as well as the D'Alembert's principle. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.